Thank you so much, John. So I'm going to lead off the presentation, and I'm going to give an overview of where we are in OpenNMT, what we've been building, why I think it's interesting, and then I'm going to end by talking about where we're heading with neural machine translation from the research community. So I'm a junior faculty at Harvard. Several of my students from my group are here. You should stop by and say hi. So I'm going to talk a little bit about my personal history with machine translation. I've always been fascinated by the problem of translation. I think it's one of the most interesting problems in the world, and one that brings together mathematical aspects, language aspects, and it's a very practical problem. I did my dissertation on this topic, and I was particularly interested in the interaction between the syntax of different languages, and how when you translate from one language to another, you have to take into account all the different syntactic transformations that can occur. This is a diagram from my dissertation in 2013, and I think the kind of main point I'd like to make is that this was pretty complicated. I was interested in all the different kind of mathematical permutations that exist when we translate from one language to another, and all the different interactions that can occur. Writing them all down in this way required solving a very technical mathematical problem, and it required a lot of computation and code. In 2014, when I was doing my postdoc, I saw this paper that came out that said, we can do translation with this model here. And this model, which is the model I'm going to talk about today in this talk, is drastically simpler than the model I showed in the previous slide. To the point that when I first saw it, I found it a little insulting in some ways, that they don't even pretend that they're dealing with real language. In this diagram, they're just translating ABC to WXYZ. And how can a model that just sets it up in this form at all kind of replicate the beautiful models that we had been building mathematically before that? But we continued to see progress on this model. And in 2015, we were beginning to see state-of-the-art results from neural machine translation models from the community. And I started as a faculty at Harvard, and I said, my group, we're going to focus entirely on trying to build versions of this model and do research on trying to understand why it works and how we can use it in practice. Now, at that point in time, I said, I'll dedicate all the resources I possibly have to this problem. And those resources consisted of one student and one computer. And this was in 2015, and we set out to kind of replicate these results. And luckily, we never told the student how hard this problem was, and so he just went and built some software to do it. And the software was called Seek2Seek 10, and we put the software on GitHub and used it for our research purposes. And when you go back and you look at the page for the software, you can tell it's written for academics because it's basically unreadable, and I don't even think it mentions the word translation at all. It was mostly concerned with the kind of modeling aspects of the underlying problem itself. In 2015, unbeknownst to us, we got an email from Paris, and the email said, we've been using your open source software to do translation. We're a company that does translation. And it was quite surprising for us to hear this, because for all we could tell, this was just something we were doing for our own academic purposes. And then in 2016, we saw this paper that came out from Systron, where they took this open source software and extended it and produced state-of-the-art results that were way better than the models that they had been using before. And doing this just from the kind of open source project we had built. And I think this really convinced me in the kind of power of having these open source collaborative communities, where academics thinking about kind of the things we think about in our mathematical world, and industry using these products for real sources could work together. And we started talking to Systron about using their engineers and using our students to build a product. And that product in particular was this open source software called OpenNMT. And so with their engineers, they were able to clean up the code that we produce. And we took it together and produced a nice website that actually mentions translation, and made the code in such a way that it was easy to use and easy for someone to get started in. And that was always the goal for us, was to make something clean, fast, efficient, and easy for people to get started with translation for the first time. Now, in 2017, we took this software and put it out into the wild. We released our first version about a year ago. And in the last year, we've seen a kind of tremendous uptake in use of this software. Over the last year, we've had almost 4,000 total GitHub stars and almost 1,000 forks of the software itself. We've also seen about 3,500 code commits from a huge amount of different users, both from industry and from academia, and from all over the world. There were 112 committers, so many of them are here today, but there are many who use the code and commit and kind of are just out there in the wild. I've never met before in my life. And we have 3 major code bases in Lua, PyTorch, and TensorFlow. So we're supporting kind of these 3 things simultaneously in the community itself. In the last year, it was ranked as one of the top 30 AI projects on GitHub. And that was just the one Lua version of the code. If you combine all 3 of them, it would be probably in the top 10 in the last year itself. And it's been used by more than 60 research papers. So this was always kind of a goal of the project, was that we wanted to support both researchers and also industry. And it's a goal we continue to hope doing today. So we're trying not to kind of focus too predominantly on one or the other. And then this year it was named as a Best Demo Runner-Up at the Association of Computational Linguistics, our major conference in the field. We can see where people are using OpenNMT. If we look around the world of where the actual usage, there's a strong usage in the United States, and actually an equally strong usage in China. And we actually have several people from China who made it out here today. There's also some usage in India, beginning to be a little bit of usage in South America, and then of course distributed throughout all of Europe. We have different stars for the project itself. And this is just for the Python version of the project. We have a similar graph for the Lua and the TensorFlow version of the project. And then, as I was mentioning earlier, it's fantastic to have contributors as well from all over the world. This map shows for all the different people who came today. So we have a lot of people using the product in Europe, in Portugal, in the United States, and also in China and India. So it's fantastic to have you all here to meet in person and not just on code contributors. I joke that I often spend a lot of time kind of waking up in the morning and trying to talk to our contributors in China, where I have to deal with a kind of 12-hour time difference in our code commits. So next up, let me talk a little bit about what it actually is that we're building, and give you an overview of what neural machine translation is and what it is that you'll be hearing about today in the research and industry talks. So first, let's talk about how you use these methods to model language from a single language. So how you might take a neural deep learning-based model and model words in a given language. This is a simple idea, and I'm going to show it to you in simple diagrams. A lot of the kind of power of these models, though, is having models that scale behind the scenes and using kind of large parameters and large computation. So first off, we start with a model of words. Here we're mapping from each word in our language to a vector representation that tries to take into account the semantic and syntactic properties of each of the words itself. We call these word embeddings, and we map from the words to these blue vectors. And I'm going to show you a little graphic of what this looks like. Let's see. Okay. So here are vectors that we took from one of our OpenNMT models. We're looking at these vectors in a 3D space. So this is the top 500 words in a language, all mapped into a vector space. If we look at each of these groups, we'll see that similar words get mapped to similar places. So, here we go. So in this cluster here, we have the words American, British, and French, if you can see here, kind of all mapped near each other in that space. If we move around, we'll see other groups, like here's troops, defense, and military. And this is the part of the model that tries to learn the properties of the words themselves and map them to be nearby in the space itself. Oops. Which one am I showing? Oh, thank you. Okay, great. So next up, we're going to combine these word representations to find a representation of the whole sequence, the whole sentence itself. And we call this part a recurrent neural network. So the recurrent neural network is going to take these word representations and try to produce a general representation of what's happening in the sentence before we do translation. And we can look at that representation too. Let me go back to my slides. And here we're seeing kind of the transformation of this vector over time, where each one of these lines represents some property of the sentence, and we're trying to represent exactly what is being encoded in the previous words in these lines. So we map from the vector space of individual words to a kind of time signal that keeps track of what properties are in the sentence itself that will be useful for doing prediction and translation. And we can kind of walk around this space and see different properties that are getting learned from the neural network model. Some of them are local properties that change over a short area, and some that change over a long period of time. Finally, we take this model and we use it to make a prediction of the next word in a sequence. So we go from word embeddings to a recurrent neural network to a prediction of the next word itself. And this is the process we're going to use to actually do a translation from a neural network. Given previous words, we consider what possible words might be next, and we search over them to find the best translation. So let's look at that in our demo. So here's our initial sentence. We start here at the beginning. The first word in our translation might be Canadian, or Ottawa, or Canadians. And then from each of these, we consider the next possible word that might come in a sequence. So here we have Canada advises nationals to stay, or Canada advises its nationals, or Canada Canada warns citizens to, etc. So we can consider each of the different predictions at each point, and then consider all of the ways we turn those in to a prediction over a sentence itself. So then we put these tools all together and we use them to do translation. So the first models people developed for translation were actually relatively simple. We would take a sentence like over the line, we would embed each of the words and run a recurrent neural network to get this yellow vector representation of the sentence itself. We'll then take that representation and use it to predict each word of our translation, one word at a time, maybe doing a search over all the possible translations for a given sentence. The next set of models extended upon this setup with attention-based models, where instead of simply just taking the word and encoding it into a single vector, we allow the model to search over words in the source sentence and select which ones would be most useful in making the next prediction of a word in translation. So here we have an input over the line, and then we want to translate each word on our right. To do this, we try to produce a distribution over each of our source words. Here we point to the word we want to translate next as line. We use that to produce a contextual vector representation that looks at the given translation so far and which words we think should be translated next. And we use that to make the prediction of our next word. And this model, known as attention-based neural machine translation, is at the heart of what we've implemented in OpenNMT. So most of OpenNMT as a project is just an implementation of this model. And most of the talks you'll hear today will be about taking this simple model, implementing it at large scale, and running it on different problems and producing translations of that form. So what we get out of this model is what's known as an intention vector that tells us which word was translated at each point in time. So here I'm showing an intention vector for a problem of summarization, where we're trying to look at which words in a long sentence should be included in a summary of that sentence itself. And as I noted, OpenNMT is at heart a simple and clean implementation of this attention-based model. each of the different components of our system consists of each of the different blocks that I've shown previously. A block to take in a source sentence, to produce a target sentence, to implement attention, and then to implement the search process that I showed you in the images before. We also are very interested in kind of the educational aspects of this, and we include documentation for each of the different components. Here are the documentation for the Python version in OpenNMT, where we have diagrams describing each of the different components, how it can be connected up, and how you can use this in your system. Now, most users don't have to dig into the details of how things are implemented, but for expert users who want to extend and modify the system, we think this is an important aspect to make it easier to use. So finally, I want to talk about what's next for the OpenNMT project and what we're thinking about implementing for the future. So this is going to be what we're going to implement from the research side of view, and I think Jean will talk more about some of the industry components and other aspects on that front. So my group in particular is very interested in extending OpenNMT beyond just machine translation to other forms of generation. So one problem we're really interested in is this problem of summarization. So given a long document, how do you produce a summary of that document, where you take into account different aspects of the summary, such as length, style, and personalization to the user of interest. So here we're kind of using a similar tool, a similar setup, but we have to take into account other aspects of this problem. We're also interested in going from other modalities. So for instance, translating diagrams into text. Here I'm showing a kind of diagram where we might produce a kind of caption that describes what's happening in the diagram. And later today, my student Yuntian will talk about some work he's been doing about doing OCR with similar methods such as OpenNMT. Finally, we're interested in data-to-text generation, how you take in different modalities such as diagrams, kind of charts or tables, and use those to produce textual outputs. So here you might kind of have large sets of data and use them to produce a textual representation. And we've started to release a lot of these models. So if you go to the OpenNMT website, we now have a bunch of different models ranging from Chinese summarization to dialogue models to some of the models for image-to-text generation and table-to-text generation. And this is in addition to all the work on neural machine translation. We're also really interested in extending the visualization tools that we've built so far. So I've shown you some of the visualization tools that all hook into OpenNMT currently, but we'd like to develop more custom tools that are particularly designed to helping us understand better what's happening in neural machine translation, and also debugging models to try to add extra features and to figure out what might be going wrong in a given model. So this is one system that our group built, and we're looking into building more models customized for OpenNMT. We're also interested in supporting other aspects of research. So there's been a lot of interesting work in the last couple of years about latent variable models over text. And we're building in a lot of these kind of research aspects into the OpenNMT system. And you'll hear more about some of the benefits of these types of models later today in the research session of the program. And then finally, one of the really fun projects we're doing is working with groups in systems and hardware to try to use and develop kind of customized ways of speeding up neural machine translation. So OpenNMT is used as a benchmark platform in several hardware specifications. And we're also working with hardware groups to actually build kind of customized hardware for the future of RNNs. So I expect kind of in the future years, there'll be kind of specialized chips in every cell phone, particularly designed for aspects of deep learning, and kind of helping be in part of that conversation of what aspects of text should be modeled with this hardware, how to make it much faster than it is currently, how to make it more energy efficient and more useful for users kind of in the day-to-day world. So that's where we're heading from the research side. And so I'll stop now and take any questions from the audience about other kind of aspects of OpenNMT or kind of what kind of research areas you might be interested in developing. Thank you very much. Yeah.
Hi, I'm Huda Boamor. I come from Carnegie Mellon University in Qatar. You didn't mention it in the map. I didn't see Qatar at all. But anyways, I'm here and I said it. It was a long flight. My question for you is about the summarization, text generation. I'm actually interested in that part of the research, and I'm wondering if it is an extractive or an abstractive summarization, which means do you go from getting the most important part of sentences within a paragraph, or do you go at the phrasal level and extract that part? So how do you? I mean, how do you? I can't find the word, formulate the problem? Is it, which kind of these works?
This is by far my favorite question. Thank you for asking it. Sorry if it's too technical for the audience. So there are two types of summarization. One is where you just cut out words from your source. You can think of that as kind of a highlighter model. And one is where you try to generate new words that kind of get the high-level view of summarization. So what we're trying to do is implement the continuum in between. So OpenNMT Pi is one of the first kind of publicly available systems that implements kind of all the different types of copy models. So these are models that allow you to do both. So you have all the flexibility of being able to generate new words while also being able to kind of pull words directly from the source sentence. So the model can kind of decide how much it wants to kind of take words from the source and how much it wants to generate new words.
Hi, I'm Marc Deymetman from Naval Labs Europe in Grenoble, previously XRCE. I have a question. There are now some new approaches to neural machine translation, like attention is all you need, or some convolutional, models, which have, attracted a lot of attention. Is that a direction that you are also considering in parallel to go towards this non-RNN, so to speak, non-sec, pure sec-to-sec models?
Yes. So it was a really good question. The question is, there have been models both from Facebook and Google this summer that kind of changed the style of machine translation. So what we've done in our software is we've implemented both of these now, both convolution and attention is all you need. In the Python version, we're still slightly behind on performance, although we've equaled performance in the TensorFlow version. It's a heavy area of research. And if you look in our forum, you'll see tremendous amount of conversation about getting all the details right. One of the things that we've tried to do is implement it in a modular way such that we use the same code for both models and only kind of differ in the kind of modeling aspect. So this allows us to reuse many of the different tools in Python for both the LSTM-based model and also the attention is all you need. And the reason that's nice is LSTM is still much more robust. We know what the right parameters are. And for most problems, that works quite well. But for the problems like very big models where you want to use these state-of-the-art systems, you have to get all the details right. And if it really matters to you, you can use that and get good performance.